It's such a delight to be here. I'm really, really excited to be able to share our work with the global community about our course, Beauty and Joy of Computing, and how we're attempting to achieve CS for all through the course. Wonderful. Lest you think it's only me who creates this course, I have a trio of wonderful faculty who have been part of our development. This on the left is Brian Harvey from UC Berkeley, my colleague, and Tiffany Barnes from NC State. We've been working together for more than 10 years to bring the beauty and joy of computing to the global audience. Very excited about that. We also have a wonderful team of folks behind us: June Mark, Paul Goldenberg, Mary Fries, and Salim Tizel at EDC. And within our Berkeley, our BJC community, Lauren, Abmak, Michael Ball are on our BJC team. Bernat Romagosa is on BJC, now working for Snap, and Jens Monig is also, working for SAP, which is delightful to have those folks on our team. Let me just set some context. This is about 10 years ago, and this is the United States High School AP enrollment. AP stands for Advanced Placement Courses, and it means courses that bring college credit. You take them in high school and you get credit when you get to college. And mostly the US numbers, if you can see my cursor, are around 1 million people each are taking history, English, and science. Some people taking math. But if you look down at the far right, computer science is a very, very small fraction of those people taking the course. And when you zoom into that box, it's even worse. It's very, very unrepresented of our demographics of our nation. We only 15% were young women, and only 8% of students of color. And as you might imagine, those numbers should be 50% people taking that course, and about 23 to 26% of students of color taking that. So computer science was infamous for having the most gender-skewed participation of any course in the history. This Computer Science A was the most gender-skewed participants of any course in the history of the College Board. They've been many, many years, I think more than 40 years, and there's no course that has been more gender-skewed than computer science, and we're really sad about that. So we wanted to change that. So there was a national feeling how to get computer science into high school. And the idea was you could either change the existing course. It was called Computer Science A. It is in Java, and it's mostly just about Java. It's not about the broad things you can do with computing. It's not about any other language. It's not about any other principles. It's just Java, Java, Java. So the spirit was October 26, 2008, a leader, Jan Cooney, got all these thought leaders together, educators, professors, high school teachers, people on the national stage. I was humbled to be invited to this. And in that conversation, it was, do we try to change CSA, the existing Java course, or should we create a new course? And the overwhelming majority of us said, we need to change, create a new course. The new course should be engaging, accessible, rigorous, fundamental ideas of computing, computational thinking. Jeanette Wing, obviously, in computing for the ACM, had a post that talked about the value of computational thinking as being even broader than computer science. So could we teach computational thinking to the high school audience, but also have it be a college course? Are there college courses out there? So this is impetus for college curriculum reform. Normally when they make a new course, what they do is they look around the world and they say, okay, let's say doing physics. What are all the physics teachers, professors doing in their first course, so Physics 101? What are they teaching? Then they take that, they look at the average. Could we find a course that mostly satisfies, most of that's being done? So it might be some course over here, some course over here, but I say, what is what most people are doing? There really was no non-major course out there that was a unified agreement. There wasn't a book, there wasn't anything. And so this was the idea that this was almost like the tail wagging the dog. What if we could create a great course in high school? Then professors might say, let's teach that course ourselves and let's do that. So that's actually what we did. So AP courses are a single source of national leverage. If you try to do this without having some way to deliver curriculum to the entire country, you're going to fail. It's just going to be, you're going to need a ton of money, or you're going to fail. So the idea was by partnering with the College Board, they immediately had a foot in the door in every high school. So let me show you a video very briefly of what this new course, Computer Science Principle, is all about. And hopefully the sound will work.
I see computer science everywhere. Smart medicine that can monitor your body.
National security issues.
Sonar technology to view the inside of your body.
It's saving lives. It's helping people.
Computers have transformed everything we do.
Computer Science Principles is a broad introduction to computer science.
It's not about syntax. It's about creativity.
They can read and understand how the internet functions.
By the time the course is over, they'll have several apps that wouldn't exist if it wasn't for their learning.
I ask my students to look at the world and to think about things that are in their world in terms of data.
They can actually understand how instructions are given to the computer.
We went from talking about how the internet travels and how computers started to where the first computer bug came from, an actual bug. I have people from the basketball team, football team, people in interior design, theater, tech people. Somebody takes my class, they're in the band, they want to learn about music, I'll teach it to them on a program that has to do with music.
I felt like I was in the studio just making a hit for everyone. This is what I've been waiting for forever. Just showing your flavor, just showing everything through code is just amazing.
Being able to press, enter or run and see my world pop up.
It's just like painting or drawing.
That cursor is your paintbrush.
A lot of girls are intimidated because they see computers as like a guy thing. If more girls were encouraged, then that wouldn't be an issue anymore.
You don't even think you're creative. And then you have a course that makes you see yourself as creative.
It kind of feels like a new light has turned on.
Computer science, I feel like, has really helped me with my confidence.
The biggest change I see in students is their confidence.
This class teaches kids how to think.
Computer science can empower. Computer science is a source of making that could lead to that power.
My friend and I, we just look at each other, we're like, oh my God, we finally got the code.
We have breakthroughs, we make discoveries.
Wow, a bunch of ones and zeros did that.
Coming into that class and seeing I can design my own thing is such a powerful thing. Awesome.
So I was honored and fortunate to join the Computer Science Development Committee, Computer Science Principles Development Committee. So I worked for 5 years trying to develop this course. And so that was very exciting. So we put this document together. This was the curriculum framework. You see on the top, the curriculum framework that basically launched this course to the world and to the United States mostly, but really to the world essentially. And it was funded on 2 principles. There were 7 big ideas, and these are not in any order, but to imagine a course that has creativity as one of the big ideas. I've never seen a course like that. I've never seen a course, certainly abstraction is fundamental to all the courses we teach. Thinking about data information, big data, how data transforms everything. Thinking about the algorithms behind what they're doing, programming, which actually is embodying those algorithms in code, how the internet functions, you saw that in the video, and global impact. We've had dedicated ethics courses about global impact, but we've never infused global impact into an introductory course. So I was so delighted with these big ideas. So these big ideas are kind of what we think about as this is what they'll know. The second column that's foundational is what they'll do. And we call these computational thinking practices or CT practices. So it's connecting computing to their interests and to society and to the impact. It's creating artifacts. It's not just reading about artifacts, but it's creating artifacts. It's writing code. It's creating abstractions. It's abstracting. It's thinking about how to summarize, how to generalize, and how to then create abstractions like programs and functions and modules and objects. How to analyze problems and artifacts. You build something, but then you say, well, does it work for all values? Does it only work when the list of numbers is positive? You can analyze, probe it, figure out how it breaks, that kind of thing. Can you communicate and collaborate? This is, how often do you have in an introductory course, force them to communicate? We have our students write and present in our course, and this is very exciting. And as well, collaborating. We force collaboration. This is a delightful course in so many different soft skills. We have advisory boards telling us this is a useful thing. Most of your graduates at your university programs can do, maybe the top 4 here. But to be able to have these soft skills of communication and collaborating is really valuable and often sets people apart. So to have this in a course to force everybody to do that, to get that practice, is such a valuable thing. So we're very delighted about that. I will say, so I kind of wore 2 hats. Both I was on the development committee making the framework for everybody, but I was also going back to Berkeley and saying, let's try to build a course at UC Berkeley that is hopefully as good as any in the country. So we created the Beauty and Joy of Computing. We have a logo here, little smiley face, BJC, Beauty and Joy of Computing. And what we looked at our other non-major course that we had, and it was Introduction to Symbolic Programming. Not a good name. Necessarily not going to draw people in. That's number 1. And number 2, it was all in schemes. It was all text in, text out, nothing graphical, nothing multimedia. We had no reading and writing. We weren't talking about global impact. With other things we weren't doing. We got woken up, and many people across the country and around were woken up to these are the things that need to be taught in these non-major courses. But what distinguished us, and we were delighted, by the way, that the College Board allowed a language agnostic approach. And what that means is you can choose any programming language. You want to choose Python, you want to choose Scratch, you want to choose Snap. I'll talk about in a second to use Snap. You want to choose C even. I mean, I wouldn't choose C. I think it's the wrong language for an introductory course, but if you wanted to do that and you really thought you had enough support, you could do that. So it allowed it wasn't just a list. We kept fighting. So many people said, just make a list. If you can choose from lists, we didn't want a list. We wanted to allow any new course to be created, not exist yesterday, exist tomorrow, and then be able to teach that CS principles the next day after that. So we really wanted to allow that full kind of 1,000 flowers to bloom approach. When we looked back at our non-majors course before, we asked our students, what was the most fun time you had? When did you learn the most, and what was the most enjoyable time? They all said, when we're doing our final project, we were really getting deep into code, we loved it. So we said, well, why then, if you're learning about, say, the internet, why would you just read about it and touch it? Why couldn't you program? Why couldn't you write, here's an easy API and you can call the API and program the internet? So we took a programming lens to many things. We also added things that were above and beyond the computer science principles course. We thought it was a very small course. We wanted to expand it. We had things we were teaching to our non-majors at Berkeley that we thought we could continue to teach. We were teaching recursion, and they said, you can't teach recursion to non-majors, to people who are chemists and social scientists. You can't. No, we said, we've been doing it for 30 years. We wanted to continue doing that. So we wanted to teach recursion. And I'll show you how we do that graphically. We want to teach the power of Lambda, the power of procedures as data. We came from a functional language approach. This is a scheme group we talked about. So we all knew that the functions could be data. We wanted to teach that, really important. We want to talk about concurrency, distributed computing. How does Google work, right? Talk a little bit about that as well. We use a graphical language that makes difficult coding concepts easier. We really found that a graphical language. We looked around the whole world of what existed at that space in 2008, 2009, and we found that Scratch was amazing. So we wanted to build our course around Scratch, but then we wanted to build it. Scratch was limiting. We wanted to build past that. I'll talk about that in the next slide. We also really had a course, I mentioned before, a dedicated course called The Social Implications of Computing. So having Brian Harvey, who had taught that course for many, many, many years, having him be part of our development team was so useful and so wonderful, because Brian could share all the things that he had learned from that course and the best practices there. Also, that technology isn't always a positive thing. That technology is often neutral. Facebook is there to connect people around the world who never, former high school classmates who would never see each other thanks to Facebook, but can also be there to affect elections and to monetize your social graph. So there's optimism with pessimism about technology, really being a realist in this. There's a delightful book called Blown to Bits that had just come out, and I recommend this highly. It's a free book. We wanted to make sure every element of this course is free. We didn't want to have cost be an issue. So by the way, everything I'm talking about is free. We're not trying to sell anything at all. This is all about giving this material away. The MOOC space is all in that same spirit, to give this away to the world. So this is a delightful book, and you can download the free PDF. I do encourage you to buy it, but there's a free PDF if you can't afford that. Here's some of the examples of some of the social implications of computing we talk about in our class. Will robots take your job? So every week we encourage people to do what we call computing in the news, where we go to the news, the New York Times, Technology Review, CNN, lots of things, Wall Street Journal. We'll find articles about technology and how technology affects society and share that with our students. So here's an example of talking about some examples from this article about a quarter of the United States jobs are at risk, a quarter, fully 25% to be automated out. And here's an example of making mass production with robots making lunch. And here is robots who are cleaning floors. I think this is Walmart. This is, I think, is in Amazon, one of their factories. And this is how you can now order at a fast food restaurant. You order there and pay there, and then you walk up and just get your food delivered at a fast food restaurant rather than having to talk to somebody. So they're going to hire fewer people. And so that's an issue as well. We often talk about some of the technology also, and some new hit technology. The idea is, and this particular article talks about, you now may be able to play, you have Netflix, which streams movies to you, but could you have Netflix for video games? The idea is you don't have a very fast computer, you don't have the latest PlayStation 5 or 6 or 7, but you want to play this wonderful game. Could the actual rendering engine of the game be in the cloud, and you're using just a controller, and the controller is able to send your controls, send your commands to the system, to the computer in the cloud, and then it just basically renders like Netflix the screen to you. So could you then open up, remarkably powerful graphics to people who couldn't afford the game systems at home to play that? So that's kind of this new idea. What does that mean for, the economics of that? And what does it mean for people trying to sell those systems? All those things there's always a positive and negative side to everything. Here's an example of using augmented reality to try on glasses. You don't need to try you don't need to go into your optometrist anymore. You can, virtually try on glasses, tilt your head and see how it looks on you. And people have really found that these kind of try on things, first for glasses, right? Your face is right there in your camera. That can be a very positive thing. But what might that mean for optometrists? So we always try to look at what might that mean for disruption of an economic engine for people who are doing this for companies. So that's an example of computing in the news. Let me talk about our programming language. We did start from Scratch. We found that Scratch was the most wonderful, intuitive, best designed program for new learners. People were 3, 4, 5, 6 years old programming in Scratch. We love that space. But we also found that there was a ceiling. The ceiling was that you couldn't develop functions. You couldn't write a function. You could draw a square, but then you couldn't write a function that says, that's called the draw square procedure, now do that 100 times. You had to have this code copied all around the place. People had this beautiful recursive pictures, but it was copies, like literally 50 lines of code with hard-coded the value n equals 1, calling at a same copy of 50 lines n equals 2, calling a 50-line copy of n equals 3. If you don't have function calls, you have to then unwrap that to be, here's the exact, and you can only go to level 5 because they didn't make a copy for level 6. It's a little ridiculous. So we said, we've got to do this. Well, Jens Monig was on the Scratch development team, and he had decided, he was a lawyer, but he's also a programmer. So he decided, let me see if I can make a version. By the way, Scratch was open source. So he took a version, added a feature to it. This is the beauty. It's like a beautiful example of open source, and said, here's a version of Scratch that has function calls. He partnered with Brian Harvey, and he added basically scheme. So we think of Snap, the language Snap we built, as basically like, if you smush together Scheme and Scratch together, you get Snap. And so this language, which runs in the browser, it runs on tablets, it's wonderful. Here's an example. It leverages the awesomeness of Scratch, design, the simplicity, the multimedia, the user community. I think, if you know Scratch, you know Snap, essentially. It's exactly the same interface, except for a couple of extra blocks we added. It's written in JavaScript in the browser. Here's an example that we always show about how many of you raise your hand if you like to use a for loop? Well, what if a for loop were taken away from you? Now you have no for loop in your language. Could you write a for loop in your language and have it just used? Most languages, you say, no, I don't know how to do this at all in C, where if a for loop weren't there, I don't know how to write a for loop in the syntax so that I could just use it. Well, here's us writing a for loop and then using it literally seamlessly as if it came down from the mountaintop on 2 tablets. And here's two nested for loops, and our sprite is now saying the value of that. So very rare, so this is a very powerful language. It's not just a lightweight kids language. This is really very powerful, and the students that we work with really do enjoy that. Here's an example of how we introduce recursion. We do this graphically, and I want to give a credit to Paul Goldenberg, I mentioned before on the second slide. Paul invented this demo. This is called the V demo. We love this. Let me take you through it really fast. So this is what our code looks like. Look how beautiful this code looks. It's color-coded based on what type of block you're using. These are all command blocks. They stack together like Scratch blocks do, and this is called Snap, so they snap together. So here's what's going to happen. When the flag is clicked, when I start, I'm going to go to the center, go to x0, y is minus 120 here, point up, that 0.0 is points up. Here's my sprite. This is, by the way, called Turtle Graphics. We know the value of Turtle Graphics from the folks at the Kindergarten Learning Lab. Here is, I say show, so if this were hidden, I show it, I put the pen down, I clear it, and I run the V procedure. What's the V procedure? This is a definition of procedure. This is like the def block in Python. So what it does is it turns left 20. So now the sprite turns left 20. It's a turn relative to where it is, doesn't turn relative to a global thing, turns relative to where it is. So it turns left 20. Moves out 25 steps. So it's going to move out 25 steps. It's going to run random of shapes. Already you're looking at this item random of shapes. Shapes is a list of blocks. Look at this, functions as data. I've just added 3 blocks as data, and it just runs a random version. So it basically puts some random decoration at the end of it, either a square, a circle, or a triangle in one of the 3 different colors we have. It moves back minus, so when you say move negative, it just backs up 25 steps, turns right 40, which basically means it turns right 20 now, and it does the same thing again. Okay, so let's run this and see what happens. By the way, SNAP is multilingual support. We have 35 languages internationally. When I've gone to China and given this talk, and when I show this slide and say, why are you teaching your students to program, many of whom don't understand any English, and there's no reason they need to, why are you teaching them in a language which they have to use while and if and English words for this? Why couldn't you teach them in a language, in your own language? And when I show them, I've gotten standing ovations at people in China when I show them that you could program in Chinese, fully in Chinese, in your language. They're like, oh my God, we could teach this to young kids. So we're very excited about opportunities to do this. We've given this talk in South Korea as well. Delightful. Okay, so let's now run this. When I run this, well, it went left and essentially, picked a circle and then came back and then picked a square. That's all it did. Not very exciting. This is the first piece of program that surprises your audience. Maybe you haven't run any program that has any randomness. So this is the first program many students have seen that actually has a random value. Wow, this is kind of fun. This is interesting. But it holds their attention for about 30 seconds, as they run this more times. Well, here's the interesting thing. What if you changed and run it again? Oh, here we go, triangle to a circle. Okay, yeah, it's fun for, again, about 30 seconds. What if you added V, itself, V itself to the list of things that V could choose. So now V goes left, and what if V chooses V? And if we're teaching students this, we have them stop and write down and predict what you think will happen. And this is a fun time, maybe for yourself, take a second and predict what you think could happen as a result of hitting the green flag. Okay, think about that for a second, and let's run it. Here we go, 1, 2, 3, ta-da! Well, that case, it just went left and it picked a green thing. This is like a dice, and it picked one of the green sides, and it did it again, picked a green side. Let's roll the dice again. Look what we get. At the end of the line is another V. You recall this is what a V looks like, and if you point it this way, that's what a V looks like. And this is beautiful. This is organic. We didn't tell it what to do, this beautiful tree, this little bush. It just did it. And that's part of the randomness of using this item random. And it's just a delightful way to think about recursion, where V could call V, who might call V, who might call V, etc. So let me fade this away and show you an example of running this a couple different times. And this is the first time. This is a wonderful thing to do, not as a lab where people are doing it independently, but doing it as a lecture. One of the reasons we have big lectures is it's nice to have a shared experience, where I first introduce a new topic to the class. This is exactly one of those moments where I'm sharing this with the class and the entire class goes, and takes a breath, because they never expected to see this beautiful picture. Look at this, is gorgeous. They've never expected to see this beautiful picture come out of that simple piece of code. And recursion, we believe, is the first time. This course is called The Beauty and Joy of Computing. And this fractal output is not just beautiful, but we believe recursion is the first time that students can appreciate that code itself can be beautiful. I think that V code is so beautiful and so elegant, can have, this can be drawing 10,000, a bush 10,000 circles and squares and triangles long. It's the first time they've seen that simple piece of code and that simple recursion can just do it. And by the way, it terminates probabilistically. It can run forever, sure, but the chance that it does that is 0. So it'll eventually pick a green end to all those lines, and the chance that it does it is 0, so it eventually ends. Here's an example of 3 more bushes. Just run it, and and most of the time it has small little bushes. One time only 2 here. It's small, but every once in a while it'll just happen to trip down. Every once in a while you're at Vegas, Atlantic City, and you end up, hitting the numbers over and over and over. So every once in a while it'll happen to give you beautiful output, and it's just so wonderful to see students play with this and be creative with V and to understand this. So this is how we teach recursion. We teach it graphically with fractals, and it's delightful. Here's an example from my lecture of how we teach abstraction. And by the way, I want to see whether I'm going to get to a slide or two where I'm going to actually challenge you to think about how would you do this in your language. So this is how we teach it. Here's an example from Scratch, and here's repeat forward. By the way, Scratch has since added functions, but they've only added commands, things you can do, things like this. They have not added functions that'll return values. So they're still limiting their audience, limiting their students from they argue it's confusing. We think it's not, to be able to write a procedure that returns a value. So you can't write factorial or Fibonacci. You can't even do that in Scratch. You cannot write a value that returns a value, write a function that returns a value. So here is a loop, repeat 4, move 25 steps, turn 90. What this does is it draws a very small square. Now a student copies it and puts a copy of their code here, and they show the same thing with 100. And when they do this, what do they get? They get a larger square. And you do this again, and change it to 395, and you get a much larger square. And you ask yourself, the student says, I'm done. Am I done? You say, well, look, you have 3 copies of the same thing. And one of the mantras we try to share with our students is DRY, don't repeat yourself. You shouldn't have 3 copies of the same code where only one thing changes. The only thing changes is the number. So what you should do, this is how we teach it, is you should make your own function, make your own command. Draw square of side, have the input be length. And when you're programming in Snap or Scratch, you take this block and you just drag length away and you add it to all the places you'd like to add it to your code. So this is just taking where the 25, the 100, and 395 were there, and we're saying, let's use that as a parameter. Let's have that parameterized. Now let's generalize. What we teach abstraction is generalization. It's detail removal. So the way we teach detail removal is you can now just use draw square of side 100, and you don't have to worry about how this was written. That's one element of abstraction. You also have this generalization. It'll work for any side, but still this isn't perfectly general. It's still only a square. If I want to draw a triangle, I have mostly the same code. So maybe you can make it even more general by making it draw a regular polygon. So you could talk about how to even make this more general, and we have this conversation. And they're all happy, and this is like the second lecture in the class, okay? So we're talking about how to make blocks, and they can do this. And now I'm going to challenge all of you who are programmers out there how to do this in your language. So now the student shows you this. Repeat 4, draw line 100, turn 90. What do you get? You get, again, here is a square. And then they show you this. Repeat 4, draw dash line 100, turn 90. What are you getting here? Well, this is just a dash line square. How about repeat 4, draw wiggly line 100, turn 90. And you get a wiggly line square. And I want to ask you, what do you tell your students now? What's different about those 3 snippets of code, those 3 scripts, is the green block. Does your language allow you to pass in the block as data? And many times the answer is no. And when it's no, I feel very sad for those students because you have nothing to tell your student who creates these 3 copies. I told them, don't repeat yourself. The only thing that's different is that green block. Couldn't the green block itself be input? And how would you do that visually? So we're really delighted to show you this is how we do this in Snap. You make a line drawer. Lambda, again, is the symbol of function as data. So I'm calling the line drawer over 100 size square. Again, we're hard coding 100 here. We can make it more general with any size, but I just wanted to show you the example. Repeat 4, you run the line drawer program, but you sometimes have to have inputs. This is a function that has one input. It's a monadic function. You need to pass that input somehow. So run line drawer with inputs 100, and boom, that 100 is being fed into line drawer. And now you turn 90. So now I can call it here, draw a wiggly line. And you pass in the block generically. You don't pass in with 100 because the 100 is going to be passed in later. You pass in the generic block. We've invented this visual metaphor for functions as data, which is, we call this the gray border. If you were to, I don't know, say, send an octopus to a friend, you wouldn't just go to the postal service and say, send the octopus. You have to kind of wrap it in cellophane. You have to wrap it in plastic wrap. And if you wrap it in enough plastic wrap, it starts to look thick and gray. And you obviously put food and water in there. You don't want the octopus to die. But here's the idea. If you continue to do this, this says, don't look at this octopus now, save it, and then later you unwrap the plastic and you have that. So this gray border is a way of saying, don't call draw wiggly line right now. We don't want it to call now. I want you to call it later. So call draw wiggly line later, and this is how, when you say run line drawer, this is the parameter, formal parameter. When you say run it, that's how you unwrap it. So you wrap it with the gray border saying wrap it in cellophane, don't call it now, call it later. And when you're saying run, you'll call it later. So again, this is an example of how to do this powerful idea. Most people aren't teaching functions as data to freshmen, to non-majors, to high school students. We're doing this and having a wonderful time with this. So I have a challenge for you all. This is a challenge for everyone on this call. I'll even pause this and give you some thinking about this. I want to write a function now in any language. The input is a list of salaries. Input is a list of salaries. The output is a new list in which everyone's salaries are doubled. I'm going to go around this room and ask you what your salary is, write it in a list, and then I want a new list, which is this is like the new payroll of what am I going to have to pay everybody after this. So what is the new doubled list of salaries? Okay, so double of salaries. And I usually, when I'm doing this as a professional development, I'll pause and I'll let the teachers work their way through this. So this is how we've done this in the past. And I basically see lots of solutions, but they cluster, and I usually say, go work in teams. So this is a call and nobody's working together. But if I do this normally, I would say, go think about this. And in fact, if you're watching this video later, pause the video, try to do it, and then come back. Remember, you cannot modify the original list. Salaries still has to be 1, 7, and 12. You need that for the tax auditor. You need to have that. But I want a new list. I want doubled salaries to return a new list to 1424 if you're given 1, 7, and 12. Well, this is what most people do. They have a for loop. They have some kind of for loop. If you grew up in a C world or a Java world, you mostly know how to do this. It's almost like you've been given a tool and that's all you know how to approach these things. So I'm doubling salaries using for. So this is an example of that. I'm going to make, for here in the snap, we're going to make ourselves a doubled salaries script, like a temporary variable. We call it a script variable, doubled salaries. We initialize it to be an empty list. And now I say a for loop where index is 1 to the lengths of salaries. So for 1, 2, and 3 is my index. I'm going to add, this is a beautiful abstraction, just add it to the end of a list automatically. I'll give me a list and add it to the end of it. There's a function called double, which is going to do the work to do the doubling for us. Item index of salaries is like the square bracket of array notation. It says, the array of that element. So item index of salaries, by the way, this is Snap and Scratch are both one indexed, and I argue for one indexing for people who are learning how to use programming. Zero indexing doesn't make any sense to young kids. So we Snap and Scratch are both one indexed. So 1, 2, and 3 as a list makes sense to think about that. So 1, 2, and 3, double item that, so it goes and grabs the 1, doubles it, adds it to the end of empty list. Now there's a list of 1. Grabs the 7, doubles it. I've got 14. Adds that after the 1. Now there's a 2, and now there's a 14. Takes the 12, grabs it off, doubles it. That's a 24, and adds 24 to the end of this. And I report. Let's see if this works. It does work. And I report that doubled salaries. It's a new list. I didn't touch the old one. It works. Everybody's happy. Okay, that's what most people do. Some people know about abstraction called for each, and for each is wonderful. It'll save you the worry about having to do this indexing, maybe running off the end, maybe not incrementing your index. So this is a lot easier if you use for, but basically the same 5 lines, just these last 3, the middle 2 here have changed. So again, I create a new doubled salaries list, I initialize it, and then I say for, look how this reads like English. I love this because it also reads more like your native language. For each salary of salaries. So for each one, I'm going to add double salary. Now there's no index anymore at all. I don't care about the index. I'm just going to go through this list one by one, grab an element out of it, double it, and add it to doubled salaries. Really very nice, really tight. And let's try this. 2, 14, 24. It also returns a new list where every salary has been doubled. We're all happy. And now I'm going to pause and say, can we do better? So that was 5 lines of code. One was 7 lines of code. Now this is 5 lines of code. Can you do any better? And most people, I actually was at a teachers conference and I shared this, and one teacher said, 2 lines. No, just kidding. And I pretended to get mad. And I walked over and I said, did you just say 2 lines? And he said, and he thought it was serious. He said, no, I was just kidding. I really was just kidding. And I said, why are you just kidding? Why couldn't you do it in 2 lines? And he said, well, look, you got 5 things to do. You got to create a new list. You got to create an element. You've got to do this. You've got to go process through it. There's no way you can do it in fewer. He said, there's no way. I love this line. There's no way it can be done in fewer than 4 or 5 lines. Ladies and gentlemen, 1 line. This block is called the map block. If you're familiar with functional programming, map, keep, combine are 3 of your blocks in your toolkit you're going to use. By the way, Python does this as well. This is called list comprehension. This is a single line of Python. This just says, I'm going to abstract away the processing of the list. And the only thing that's different about what I'm doing is I'm passing in, what are you doing to every element? So map is a function that takes another function, remember the gray border, as And this is a reporter. It's not taking a command, it's taking now a reporter, something that returns a value. So I'm taking this double function as an argument. I'm going to map it over the salary. So for every salary that I'm given, whatever this list is, I could be a million elements, I don't care. 1, 7, and 12. It's going to apply that function to every element and return a new list in which the output list has that function applied to every single one by one element of the input. And this is how we do it in Python as well. This is a delightful abstraction. This is abstracting away the processing of it. So we think about abstraction as a powerful idea. We think of this is part of teaching abstraction. And by the way, nobody else. There are 10 or 12 different computer science principles courses. No one else teaches recursion. No one else teaches functional programming. And by the way, students have no trouble with this. They still have trouble learning recursion. Recursion is one of those hard ideas, and some people still have trouble by the end of the year. But we found that if you do this in this graphical way, I taught a middle school class, and I'll talk about this a little later. A middle school class. I had a 4th grader, 5th graders, and 6th graders, and they were fluent in map and keep and combine. They were able to just do it. It's just a delightful problem if they can think about this. Really, really remarkable how accessible this material is if you start early and start easy and just work through that. There's 3 things you got to learn: map, keep, and combine. And you can build your own. You don't have to. You don't ever have to get to that level. But the idea is you can do so much processing if just have map and keep and combine as your toolkit. Let somebody else do the hard work. Let somebody else worry about incrementing the index variable. Let somebody else work about the for each. And all you're doing is passing in a function. If you can think about this, all of a sudden programming becomes lighter. I'm almost arguing, and Jens argues this as well, we should keep adding more and more layers of abstraction so that you're not, the analogy he used, which I love, is if you're doing this yourself, if you're kind of manipulating the lists and you're changing the pointers, you're down grinding with the pigs. You're down there in the slop, and you're there and you're getting muddy and dirty. Jens and I and all of us on BJC want to be up flying with the birds. You're flying above all the details of how you have to manipulate the list and make a new list. Just fly above it to what you want to do. I want to double every element of this list. Fine. I use map and I'm still flying above it, and all the details of how it's done are below my level of abstraction, hidden from me. Wonderful, wonderful, very powerful. So let me step back and talk about we're almost done. I have about 10 minutes left before we take some questions. Let me talk about some of our impact. So this is the graph. This is Brian and I, and we taught together. This is the first 3 courses, the 60 series and 61 series. We went to Berkeley and we said, we need all the data on gender diversity for our computer science courses since the beginning of time. Berkeley's, I'm 52. Berkeley's 100 years older than me, exactly. So Berkeley's 152 years. I said, go back 152 years. I know there was no computer science course the first year, but I want you to find all the data you have on gender diversity. They said, you know what? Can you believe we only started keeping gender of our students in 1993? We went, really? Well, all right. So this is the first piece of data we could ever get from Berkeley. This is 1993 spring. This is the diversity and gender of our, and I'm going to say this top 2 lines are our course CS3 and CS3L. I was at Berkeley since 1990, so I was here during that time as a graduate student. I've been here 30 years. So the top 2 lines are non-majors course. The bottom 6 lines, we changed the name of it, we changed the content, but mostly it's the same. It's our first course, A, B, and C, our first course for majors, okay? So notice how the top course wiggles and wiggles and wiggles. By the way, I was part of the teaching community as well. So starting in 2000, right around here, I was teaching the top courses and the bottom courses as well. So when you do a study, you want to change as few as things as possible. So I was the one teaching these courses. So the numbers wiggling, if you look at this, about 35% young women in the non-majors courses, and really, up and down, down to 10% here, but up to maybe 30 at the high, around 20. It averages around, up and down, basically the bust and boom of the .com bust and boom. But you're noticing it's around 20%. So we're looking at 20 and 35% young women in our intro courses since recorded time. We introduced Beauty and Joy Computing. And if you look at how we wiggled around 45%. And for the first time ever, we crossed 50%. I was so delighted. I couldn't believe it. I was just, I gave a keynote like this and I said, we've never ever achieved 50% women in a computer science course at Berkeley. And we have now, and it's so remarkable. And then, a funny thing is, I looked a couple of years later, we were at 65%. The number had continued. Turns out the actual details are 63, but still 65, rounding up to 65%. Amazing numbers of young women taking this. And in fact, fact, we draw from our population of students. We have a culture of student teachers. When we think about who our teaching assistants, our readers, our graders, our lab assistants are, these are among, I'm also kind of a hack photographer, so these are some of the portraits I've taken that I put on our staff page for the young women who've joined our team. Look at those smiling faces, remarkable young women. Remarkable to be a young student and look up and see the students that your teachers look like you. Really delightful. And this is happening all around the country. The number of students, here's the number of female students, total number, and the percentage of female students taking overall APCS exams. This is, I think, a year out of date, but still pretty remarkable. This is the total number of underrepresented minorities. These are students of color in the US. And this is, again, the percentage of that. And again, we're not there yet, but we're creeping up, and we were flat. We were flat for so many years at 20%, and we're now approaching 30 and even hitting 30 in the last recent years. And the numbers are growing wonderful, and the percentage is growing. So not just the total number of students we're reaching, but the percentage is growing, and we're very excited about this. We're doing actually better in terms of reaching underrepresented minority than we're all reaching women. I mean, we need to hit 26% in the US. We're almost there. We're doing a great here, but we're not doing so well with female students. So we have to do more work. We have work to do. We're not resting on our laurels. We have work to do in terms of getting this course into everybody. There is a national challenge, at least in the US, of what if here's the problem. The number of PhD candidates is basically remaining flat. This was a New York Times article. But the number of undergraduates who are going into computer science is unbelievably exploding in a way we've never seen before, from 30,000 to 100,000. So it's going, and the CRA just released a report where it's basically everyone's seeing at least a 4 times increase. At UC Berkeley, at these state schools, you often see a bigger, and our number is, we're 11 times bigger than we were at the low point here. 11 times bigger. Imagine taking anything and scaling it by a factor of 11. Things are going to break and bust and burst at the seams. I make an analogy. Imagine Bruce Banner's clothes before it becomes the Hulk. If the Hulk grows 11 times bigger, everything's going to be breaking at its seams. And many of us are having struggles just to manage that onslaught of students. So there is a concern that we're not ready for an onslaught of this continues. If we continue to excite students in high school, but not provide for them and make it more difficult for them to take these courses and have the intro course. Our intro course at UC Berkeley, we believe, is one of the largest in the world. 2,000 students in one course, one professor, an army of TAs, and we have 2,000 students. So we're having challenge with scale, but we're actually using some of the technology with MOOC to be able to work with that scale. So we're delighted about that. I'm almost done. Recognition for our success. We were happy to be, I've been very fortunate, honored to be featured on the front page of the San Francisco Chronicle to talk about some of our success at reaching young women. TechCrunch pulled that up and mentioned this. So again, I went on some keynote, I mentioned that we had reached 50% of young women, and then somebody tweeted it, and all it takes is social media. That tweet went viral. All the newspapers called up. My phone was running off the hook for a little while. Slate picked it up. Hacker News picked it up. This is, again, on the front page. Here's me on the front page of the San Jose Mercury News talking about this, very excited. And again, they had another article about this as well. So these are all my students. So long story short, we were very honored about all this national press, actually international press we received. We were on the front page of the New York Times one day for some of our work we had done. We reached, actually the numbers updated, the intro said we're at, I think, 500, 600. We're actually at 800 or more. We believe we're actually crossing 1,000 if you count internationally, who we've reached. 800 students, teachers, and professors all around the world. I'm very excited to reach. This is professional development we've offered around the country. This is some of our teacher community that we teach on Berkeley. Here's me in the middle, sharing a BJC with some of our teachers. We went to Peru last summer to share this with some teachers, or 2 summers ago to share this with some teachers. Delighted to see that national exposure. This is an example of this bringing to India. Delighted to have folks in India take up the BJC cause. This is delightful here. We wanted to also give back. So in terms of our national outreach, we got a couple of National Science Foundation grants. I want to make sure I mentioned that. We partnered with EDC. I mentioned the people we worked at EDC with them. The demographics of New York City are remarkable. New York City is the largest school district in the world with more than 1 million students. If you look at these numbers, here we're looking at 70% students of color, remarkably diverse. In some ways, remarkably not diverse. You'll have an entire school with not a single non-student of color. So sometimes it's not diverse. It's diverse in some ways, but not diverse in the sense that it has everybody in the conversation. But we wanted to go back. I grew up in New York City. I wanted to give back back to New York City. Here's a logo, BJC Loves New York. And so we were so happy to be able to work with, we got a big grant to be able to work with New York City teachers. We brought 100 teachers, and actually we doubled it. Now we're at 200 teachers out of that. And part of the reason we're at 1,000, we reached 800 there, and that's not even counting New York City. If you add New York City, we're at 1,000 teachers total. This is a conference about a MOOC, so let's talk about this. We built a MOOC some years ago, and we had this MOOC active for 3 years. We believe it was the longest MOOC at the time. It was a year-long MOOC. The idea was you'll take the MOOC and be in your high school. What if you were in high school and wanted to learn computer science but have no high school teacher? Well, we built a year-long, most MOOCs are like 8 weeks, 6 weeks, 12 weeks max. This was a year-long MOOC broken up into different pieces. And at our peak, we had 16,000 people in our MOOC. We were very excited about that. It's now available as a self-paced course. Armando Fox, my colleague, has talked about the value of a SPOC, a small private online course. This is a hybrid course. You can think of it as an ebook. You basically take the MOOC and use the resources in your classroom. I don't need to tell this community that, but it was a wonderful, our high school community, our high school teachers are now using our MOOC in there thanks to edX. So again, thanks to them for that source to do that. I want to just share the delightful partnership we've had with Universidad Galileo. BJC has been translated to Spanish. We're still working on that project, but we're almost done. We're really excited about it. And again, gracias to Hector and Rafael and the group for all the work they've done to bring BJC. If you're a student who doesn't speak English, you don't have access to BJC. BJC is this wonderful, high school curriculum, but if you can't read English, you have access. So we wanted to break down that access. We're so excited about this, to be able to work with this team to bring BJC to, again, a more global community. We're excited about offering professional development this summer, in which I mentioned before, SNAP is multilingual, so SNAP will be in Spanish. The curriculum's in Spanish. All the teachers will be in, teaching, speaking Spanish. All the students can be in Spanish, all the support. So the idea is, could we expand to the Spanish-speaking world to bring BJC to everyone? We're excited about that. I was interviewed by TechCrunch and asked, what are the keys to the course? So this is for all the educators here. What are the keys to making a non-majors course really work? I'll just briefly say this. Pair projects work amazing. You make your students pair up so that they're never feeling alone and isolated. Have students choose their own projects. Don't give them a project. Don't give them tic-tac-toe or Tetris or something, or let's implement something, breakout. No, let them choose their own projects and let them use their interest and their agency. Have them read and write about social implications of computing as well. Don't just talk about coding. Talk about the social implications as well. Make sure your class is accessible. Everything is free. Make sure you have your class have active learning. We use clickers in our class. We give the clickers away. We got a grant. We give them to our students, at least at Berkeley, and we do this, and people can do other things online as well. Don't have a sage on the stage, but a guide on the side. We have 4 hours of lab a week. It's not about talking at them. It's have them engaging with the curriculum, working through that. Many opportunities for students to give back as lab assistants. Do you have a way for your STAR students to come back as a TA or a lab assistant to help your former class? My son asked about this. My son took a BJC course, asked his high school, could I give back? They said, sure. He's now a TA for BJC. My son is only 15 years old now. He's a teacher helping other students learn BJC. I'm so proud of that. The programming language is graphical and quite pretty. We just love that without being dumbed down. And we, as much as possible, we believe the course and curriculum really does help capture the beauty and joy of computing. Finally, this is like the penultimate slide. The lessons learned overall, graphical languages lower beginner frustration. Go with a graphical language if you have a non-majors course. We really found that works very well. You can teach powerful computer science ideas in CS0. They said it couldn't be done. They said you can't teach recursion. You can't teach functions as data. We're doing that. Students are learning it and being engaged. Think about a functional approach. People mostly start, here's a for loop, here's this, here's how to take a variable and change it. We're thinking about a functional, a scheme-based approach in which you're thinking about functions that return values and try not to have mutation in the early stage. Think about a functional approach. We found that really does work. Bring computing in the news to every single course and ground your course with news of the day that's relevant to computing and relevant to that course when you can. If you're teaching an AI course, oh my gosh. I can't imagine that people teaching AI aren't doing this every day, because it seems like every day there's this. This is once a week we're advocating, but at least once a day. And celebrate our diversity of students. Don't have a weeder approach, but think about the diversity and celebrate that diversity of students. Bring a big tent. And we've never, in 10 years, we've never turned a single student away from BJC. We always ask the department, can you give us some more money? Can you give us some more money? And even though we're strapped because of all the student desire to take these CS courses, they've been able to give give me more staff to grow the class. Never, ever turn a student away to our course. We never want to have that happen. So again, consider a big tent and celebrate the diversity. In summary, my last slide. Thank you so much for this opportunity to be here and share the ideas of BJC, share the idea of the BJC MOOC and the SPOC and the connection to BJC and Espanol with you. We believe that BJC, CS Principles, and SNAP has been transformational for myself, for our teachers, and for all the students there. We believe we have reached 20,000 students teaching this. I mean, for people in the MOOC community, that's not a big number. For people who have not been in there, that's a big number. We're very delighted with all our international impact. We stand on the shoulders of giants. Really, this isn't all about rah-rah what I've done. It is really about what other people have done. The CS Principles framework, I was part of that, but really it was a whole community of teachers and professors building that amazing framework. Scratch, I haven't touched that. I mean, I know Scratch, but I haven't been part of the development community for that. It's an amazing community. We love what they've done with Scratch. We honor them, and we stand on their shoulders. They're amazing. Blown to Bits is an amazing book. We reference Blown to Bits, I feel like every week, talking about, this is from chapter 6, this is from chapter 2. Blown to Bits is a powerful book. Bring it to your class if you can. Delightful book. And I think they even have a version 2 coming out soon. Our summertime PD is all-time total to 800. If you include New York City, that's now at 1,000. So we're at 1,000 teachers we've reached. We're so delighted to have reached at this international community of teachers doing this as well. And the future is, we're so proud of our future, thinking about going to bringing BJC to the Spanish-speaking community, bringing BJC to middle school, working on that. I should mention that. That's very exciting for us. How could you even go younger with BJC? Our future is so bright, we have to wear shades. Folks, thank you so much. My name is Dan Garcia. Delighted to be able to be here and present.